All right, let's dive in. Today, we're cracking the code on C functions. Now, these are the absolute building blocks, the single most important tool you have for writing clean, powerful, and most importantly, reusable programs. Seriously, if you want to move beyond just simple scripts and start building something real, you've got to master functions. So let's get into it. So let me ask you something. Have you ever been coding and you find yourself just copying and pasting the same lines of code again and again? Yeah, we've all been there. It's that classic sign that your code is starting to get messy, tangled, and really hard to maintain. Well, the good news is there is a much, much better way. And that better way is the function. The best way to think of it is like a mini program that lives inside your main program. It's a totally self-contained, reusable block of code, and it's designed to do one specific job really well. This isn't just about fixing the copy-paste problem, This is the very foundation of how we do structured programming. So why even bother with them? Well, for one, functions help us stick to the don't repeat yourself principle, or DRY, as you'll often hear it. But more than that, they take what could be a huge, tangled mess of code and help you organize it into these clean, logical blocks. So instead of one giant, impossible-to-read file, you get these small, names pieces that are way easier to understand, to test, and to debug all on their own. Okay, so we get the why. Now let's get our hands dirty with the how. We're going to put a C function right under the microscope and break it down piece by piece so you can see exactly what makes it tick. For this, we'll use this super simple add function. I mean, as you can probably guess, it just adds two numbers together. But don't let its simplicity fool you. Inside this little function are all the essential parts you'll find in every single C function. Let's pull it apart. The very first thing you see right at the beginning is the word int. That's the return type. You can think of it as a promise the function makes to the rest of the program. It's promising what kind of data it's going to send back once it's finished its job. In this case, our add function promises it's going to return an integer. Next up, we've got the function's name, which is add. And right after that, inside the parentheses, we have its parameters, int a and int b. Think of these like the ingredients for a recipe. The add function is telling us, hey, to do my job, I need two integers, and inside my little world, I'm going to call them a and b. And finally, the part inside the curly braces. That is the function body. This is the engine room, right? It's the actual set of instructions that performs the task. Here, it's just one simple line, return a plus b. It does the math and then uses that special return keyword to send the result back out. Now, this is a super important point in C. There's a big difference between telling the compiler about a function and actually showing it how that function works. The declaration on the left, that's just a promise. It's a signature, ending with a semicolon that says, hey, compiler, trust me, a function with this name exists. The definition on the right, though, that's you making good on the promise. That's the actual code, the implementation. So that's the blueprint, but a blueprint doesn't do much good until you understand the mechanics, right? So now let's look at how data actually flows into and out of these functions while your program is up and running. When you get down to it, user-defined functions pretty much come in four flavors. You can have a function that takes in some data and also returns a value, just like our add function up in the top left. Or you could have one that takes nothing in but still returns something, maybe a function that gets input from a user. Then you've got functions that take data in but don't return anything, like maybe one that just displays something on the screen. And finally, you've got the kind that does neither, like a simple greet function that just says hello. Okay, let's get our vocabulary straight, because this trips people up. The variable inside the function's definition, like x here, that's a parameter. It's just a placeholder. The actual value you hand over when you call the function, like n, that's the argument. A good way to remember it, the parameter is the parking spot, the argument is the actual car you park in it. Now, by default, C uses something called passbyvalue, and you have to understand this. It means the function gets a copy of your data, not the original thing itself. It's like you're giving it a photocopy of a document. The function can scribble all over that copy, change it, do whatever it wants, but your original variable, n in this case, is totally safe. It's still going to be 5. But what if you actually want the function to change your original variable? Well, for that, we use passbyreference, which in C means we're going to use pointers. So instead of passing the value, you pass the variable's actual memory address. This is like giving the function the key to your filing cabinet. Now it can go directly to the source and change the original document. And that's exactly why n becomes 25 here. All right, for our last topic, we're going to talk about a concept that might feel a little mind-bending at first. But trust me, it's one of the most elegant and powerful ideas in all of programming. We're going to dive into recursion, the art of a function calling itself. At its core, recursion is really just a way of solving problems. A recursive function takes a big problem and says, I'm going to solve this by calling myself with a slightly simpler version of the exact same problem. It keeps doing this until the problem becomes so simple that it can be solved instantly. Now, for this to work without just exploding, it has to follow two absolute non-negotiable rules. First, you need a base case. This is the stopping condition. It's the point where the problem is so simple, the function just knows the answer. Second, you need a recursive case. This is where the function calls itself, but, and this is the critical part, it calls itself with an input that gets it one step closer to hitting that base case. And I really can't stress this enough. You have to have a base case. If you forget it, the function will just call itself and call itself and call itself forever. It'll just keep eating up memory until your whole program comes crashing down with what's called a stack overflow. This is the #1 rule of recursion. Don't forget it. So let's watch this happen with a classic example calculating a factorial. When we call factorial of 4, the function basically says, I don't know that, but I do know it's just 4 times whatever factorial of 3 is. So it calls itself. Then factorial of 3 does the same thing. It calls factorial of 2. And this chain reaction keeps going down and down until we finally hit factorial of 1. And this is our base case. The function knows the factorial of 1 is just 1. It doesn't need to call itself anymore. It has a concrete answer. We've hit the bottom of the rabbit hole, and the chain of calls finally stops. And now the really cool part begins. Factorial of 1 returns its answer, 1, back up to factorial of 2. Now factorial of 2 can finally solve its part of the puzzle. 2 times 1 is 2. It returns that result up the chain. Factorial of 3 gets the 2, calculates 3 times 2 is 6, and returns that. And finally, our original call, factorial of 4, gets the 6 and calculates 4 times 6 to get our final answer, 24. And that's recursion in a nutshell. It's this elegant cascade, a dive down the call stack to find a simple answer, and then a climb all the way back up, building the final solution one step at a time. So there you have it. From those simple building blocks to the mind-bending elegance of recursion, functions are truly the heart of C programming. But you know, that elegance can sometimes come with a price, usually in memory or performance. Which brings me to a final question for you to chew on. When is a beautiful recursive solution the right way to go? And when is a simple, no-nonsense loop the smarter choice? That's all for this one. Keep on coding.